It's David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. We're reviewing test number 3. Second problem set up was truss analysis by the method of sections. We had a triangular shaped cantilever truss, 4 bays or panels as I call it, and the configuration was this. To talk about a little bit on the geometry, we have 4 bays at 1 meter each, so it's 4 meters long, 4 times 1. All I was given over here was 2 meters. You should realize by similar triangles that I've got 4 panels vertically also, and so I just divide that 2 meters by 4 and I get each panel is 0.5 meters. So from A to B vertically is 0.5, 0.5 from B to C, and so forth. So that helps me as I've got to know my geometry and set up these problems and solve them. Okay, I was asked to find the member forces at BC, BH, and GH. So looking at my truss, that means I need this one, BC, BH, GH. So I want to cut a section right there. And remember, on the method of sections, I don't have to solve for the reactions, and sometimes all of them, or sometimes I don't need to solve for any of them, depending on which part of the truss I look at to analyze. Okay, so I can see if I analyze the part of the truss to the right of that section cut, I don't have to deal with the reactions at A and F. So that's what I'm going to do. I'm going to cut a free body, draw a free body of the part to the right of my section cut, and here it is over here with my member forces, with my unknown member forces, BC, BH, and GH cut off, my forces, a little bit on my dimensions, and I want to work out what the slopes of BC and BH are. And so for BH, it's going from H to G, so that's going over 1 meter, and it's going up 3 panels. 1, 2, 3, so that's 1.5 meters, 1.3 times 0.5. So it's going up 1.5 and over 1. Do the Pythagorean theorem, I get that the hypotenuse is 1.803. Similarly, I look at member BC, it's going over 1, and it's going up just 1 panel, 0.5, so it's 1 and 0.5 up. So the Pythagorean theorem gives me 1.118 for the hypotenuse of that one. Now I'm all set up, I know my geometry. I can, as usual, sum moments to solve for as many as I can. First one I'm asked for is the force in GH, this one down here, this horizontal member down here on the bottom. I take some moments about point B, which is not even on my the section that I'm using, but I can still sum moments about it. It's right up here. I've kind of dashed in those lines. It's where BC and BH intersect, that's why I chose it, because it eliminates those 2 forces from the calculation. All I have to deal with the force in GH, and I'm summing moments about point B up here, so that's 1.5 above, vertically above GH. So and GH is trying to rotate clockwise, which is negative by my sign assumption. So I get FGH times 1.5 negative minus this 3 kilonewton force here, 1 panel or 1 meter over from B. It's also trying to rotate clockwise, so it's a negative number. And also negative is my 6 kilonewtons out here times 3 panels or 3 meters, trying to rotate clockwise. Just do the math. I get FGH is equal to negative 21 divided by 1.5, so that's equal to negative 14 kilonewtons, so that makes it compression. So I report my answer as 14 kilonewtons compression, and I want to go to my free body diagram and reverse the arrow because I've assumed tension, and show that the real direction of FGH is pointing at the joint, so it's because it's in compression. Okay, now I can go to the top and solve for the force in BC. A little blow up of the geometry there. Here I've got my slope relationship for the member BC, 0.5 and 1 and 1.118. And I broke it out into components because I'm fixing to some moments about point H down here, because that eliminates BH and GH, which intersect there. And another good thing is it eliminates the vertical component of FBC, because that's at point C, and that's passing through, the vertical component of that passes through H also, so I can eliminate that. I can also eliminate my 3 kilonewton force up there because it passes through point H. So I'm left with just the horizontal component of FBC, which is 1 over 1.118 times the force in the member. And its distance, the vertical distance from point C to point H is that 1 meter. 2 panels, 2 of those 0.5 meter panels. So that's the moment it's trying to rotate by my tension assumption on the top. It's trying to rotate counterclockwise, so it's positive. And then I have the 6 kilonewton force trying to rotate clockwise or negative about 0.8, so that's 6 times 2 meters. So FBC is equal to 12 times 1.118, and that's equal to 13.4 kilonewtons tension. So I'm ready to proceed on to the force in BH, which is this diagonal member here. We worked out the geometry of it, and so I can either do I could do a sum of moments about some point. I guess I saw somebody did sum of moments about point E, which is pretty clever. It eliminates GH and BC and the horizontal component of BH, but I've chosen to do sum of forces in X. Positive to the right, I've got three forces that are in the X direction. The negative of the horizontal component in BC, which I just solved for, negative 1 over 1.118 force in BC, which is 13.4 as I solved for there, plus the 14 kilonewtons in GH, which I have set, reversed that arrow to make it remind myself that it's plus to the right, and minus the unknown. The X component, horizontal component of BH, is 1 over 1.803 FBH. Do the math, negative 12 plus 14 minus that, so 2 minus that is equal to 0. Put that on the other side of the equal sign. I get FBH is equal to 2 times 1.803, 3.61 kilonewtons tension.